we'll start. Thanks everybody for joining, and a few people joining in. It's a pleasure to have Richard Kollar present. He's presenting now from Bratislava, Slovakia. This is our first underseas seminar presentation. So Richard is an eclectic applied mathematician working on a variety of things in applied mathematics. And in the past few months, like many of us, he's been heavily involved in COVID. He's actually in the Slovakian crisis management team, also advising the government. And he'll show tonight work with a co-author, Katarina Budova. So thanks a lot, Richard. Well, the floor is yours.
Yeah, thank you, Yoni, for inviting me and giving me the ability to speak on our, most recent results on COVID-19. So let me just start with a brief overview of the situation here in Slovakia and how I got involved in this. So I'm mostly math modeler. That's what I'm considering myself, and math analysts. And this seemed to be a really interesting topic to work on, especially because Slovakia was in a very special situation. We got the lowest rate of the deaths and probably also the patients in Europe. So some way the progress of the pandemics in Slovakia was a really huge puzzle for many of us. And the first predictions of the Institute of Health Policy, it's a government institution, the numbers were high, as the predictions of Ferguson in UK and other studies. And it really made me to think about the problem and to get the numbers right. Also, actually, this Institute of Health Policy, they contacted us, and so we helped to develop their tools. And which now is the tool which is used for predictions in Slovakia, at least. So we worked on one side that was basically some modified SIR type model. But to tell the truth, okay, I was designing that model, but I was really some kind of skeptical about using that model to model the data, especially the real data we were getting from the testing. So I got involved with this project with the Institute of Health Policy, and then we actually tried to make some kind of public campaign on Facebook and through other means with the help of some economists in our country to get the information across that how the pandemics behave and what is the safe practice and so on and so on. So some way I got hooked up with this crisis management team at our government, which is composed mostly of friends of the Prime Minister. These are all scientists, but mostly these are handpicked people, and these people were some way ruling and really some way, how would I say, really managing the response of the country, at least at the beginning. But as I said, our country now is one of the with the lowest rate of deaths and lowest rate of everything actually in Europe. So it's changed. The role of crisis management is still lower and lower. We opened up the economy almost completely. We still have closed borders, but it's getting open soon as well. Almost everything is almost in the up to the normal now in the country, and so it's now just the regular politics. So the science is not anymore the basis. You can imagine probably in Australia it cannot be very different, in many other countries as well. So the role of some way the science is decreasing, but I see it quite differently, because I see actually right now maybe we can provide some more information, and I think the information I will provide today may be quite helpful for understanding what is going on. So let me start with the major part of it. And the talk will have two parts. One is the project, which is some way finished. We published the preprint and submitted a paper some week ago, I think about 10 days now, and we wait for the response. but the second part is quite new, and that may be more interesting, and it's also more controversial. We will see. You will see later. So the first part is the data analysis. The second one is more modeling, and I really think the second part is more interesting. So if it's a teaser for you, yes, stay till the end. It may make it really heat up the discussion a bit. So this is the work with my collaborator and wife, Katarina Bodova. We work at the same university, and that's what it is. So let me now go to the next slide. How do I do the pages? Okay, so this one. So COVID-19 data. Probably almost all of us are looking daily on different types of data. You can see them in the table over here from water meters, and there's a lot of numbers. Really, the number of numbers is huge. And one question which arises is how to manage all this flow of numbers and how to understand them. So I'm really trying to address this question primarily, not the sources, but at least what the numbers are telling us. And at the end, I will again come back to what they don't. So really, our first try was to understand what is in the data and how to understand the data. Okay, we're not looking, of course, at the table itself. If you download the data and then you just look at curves, on the curves. And one of the curves you probably recognize. This is Australia, pretty recent data from water meters. And the curve shows the number of active cases. Active cases, as you know, is the number of positive confirmed tests, RT-PCR tests. And from the number of positive tests, you subtract the number of people who are officially recovered. That typically means that they had 2 consecutive negative tests of the same type. Plus, you subtract people who died and had COVID, or not COVID, but SARS-CoV-2 confirmed by the test. So this is the curve, and the curve has a couple of significant features, and we will be concerned about these features. Yeah, so of course, right now the curve is almost behind us, and we may discuss, what's the reason of the decrease and how fast it declines. But mostly we were concerned about these curves at the time when the curves were growing. Okay, so now actually my point of view will be, what if you are in one of the countries when the things are growing suddenly and you don't know where's the peak? So can you say something about the peak? Can you say something about the, what stage of the epidemic you are right now, and so on? So that will be the major question. And also, you want to some way predict the future. So for this is just understanding of the past, but you need to view it as the prediction of the future to some extent. Also, you may think about it. This is like some type of analysis of the future, possible next waves, if there will be some. So that's the way actually to look at it. So as we all know, very likely is that the traditional SIR models, which proved to be really efficient and very well describing the previous epidemics of various types, they predicted that at the beginning, at least, of the epidemic on the onset, the growth of the number of these active cases will be exponential. Okay, this is a really short asymptotic calculation from the model, and it's easy to see. And here is the example of couple of 2 countries. It's Afghanistan and Bolivia. These are quite recent data, not completely recent. I think these are up to the May 5th, so it's 20 days late. So behind that, and these are both active cases for both countries in 2 different plots for each country. The plot on the left is the semi-log plot. So it means the vertical scale is logarithmic, but the horizontal scale is just linear. And the plots on the right will be the log-log plots, double log logarithmic plots. So that's logarithmic, both the date, also date time is scaled logarithmically. And as it's easy to see that the linear trends in semi-logarithmic plot are corresponding to exponential growth, while the power law growth or polynomial growth is captured by the linear growth on the double logarithmic plot. Okay, this is pretty simple thing. And as you can see, Afghanistan and Bolivia are not doing very well. At least they were not doing very well on the May 5th. As you know, the data were showing that they really still had some exponential growth in their country of the number of cases, which is not good. Okay, we all probably agree that exponential growth is probably not that good, especially when you're growing, like you double the number of cases in a couple of days. So that's not good. As I said, this is some way expected from the SIR models, at least at the beginning of the pandemics, on the onset. And first predictions of the spread of COVID-19, or not the COVID-19, not the disease, but of the virus, of the coronavirus in the society, in the population, were some way saying that the SIR models are great, and at the beginning we expect the exponential growth, then that will slow down, and then we will go to exponential decay. Okay, so, but the data always show some different story. If you look at the data in almost every country in the world, especially this was in Slovakia, because I was really concerned about Slovakia, as everybody here, the growth was not exponential. You know, it's hard to tell what is an exponential growth and what is the power law growth. But you know, as you can see over here, like the case of Indonesia, you see some kind of slowdown, exponential slowdown, and you may say, "Oh, it's a change of the exponent of the exponential growth." But if you do the log-log plot, you see that actually it may be a power law growth, power law trend, and this was observed in probably every country in the world. There was a transition from the initial exponential trend to the power law growth. Actually, in countries like Slovakia, we didn't even have the exponential trend because we made all the measures, you know, all the mitigation measures were implemented right on the onset when we had 1 or 2 confirmed cases. So we skipped the exponential phase, and that was really part of the success of the country. We may discuss that later. But what I'm saying, you know, there's a really pretty clear trend, and in some countries actually it's more pronounced, in some less. And the power of this power law or polynomial growth differs by the country. As again, many of you may know, this is kind of tricky thing, because to estimate the power of the polynomial growth, it depends where you start. So somewhere in our analysis, the starting point is somewhere systematically selected, and we scale the starting point in such a way that it corresponds to the size of the country. You need to avoid some low data, because that's some way it's not very reliable. But afterwards, actually, you do the scaling according to the size of the country, and then you should get some systematic approach. Okay, so we see that Argentina and Indonesia are doing somewhat better, because as we know, power law or polynomial growth is much slower than exponential growth eventually. So it seems they are behind the worst. I'm showing 2 more countries over here, is Russia and Somalia, which actually show as well some, at least on the May 5th, they were showing some signs of power law growth or polynomial growth. What is really important to say, this is not in agreement with simple SIR models. If you take the SIR model, it really cannot sustain the power law or polynomial growth for a longer period of time. So you may do some modification in SIR model, some way to enforce this type of growth. It's possible, but the naive way to look at the problem and the data doesn't allow that. But as I said, this is actually not just us, of course, observing this polynomial growth. You heard about it. There are plenty of studies around which actually show this. We observed it very, very early in, I think it was like very early March. We submitted a study to Lancet and didn't get a response in like 2 weeks or 3 weeks. And, during the time, many other studies appeared, and then we got a response that they're not interested. So it's really funny, how this works. But nevertheless, the science works differently now, for sure, in this period of time. But the thing is that many studies observe this trend, and some way it's believed it's a thing. It's not something we just make up over here. Again, it's a stage at which the country is, and probably Somalia and Russia, they wait till something else happens and they will get better and they will reach the peak and so on. So here I'm getting to the interesting part of this data analysis that we were lucky to go, to see. So some way, even in March, we both, me and my wife, we worked at the University of Michigan, previously, and a collaborator of us from Michigan, Robert Ziff, who works in complex systems in Michigan, came up with a study. I will show some data from his study, where he pointed out that there is a other regime at the end in many countries. That time it was just China because nobody else was that far in the epidemics, in the pandemic. So, and you can see it in the formula here in the bottom of the slide, which shows the number of infected, so that's the active cases, is actually a combination of power law growth, that's the T over TG, the T is the time, times the decaying exponential. And TG is some kind of a time scale, which characterize, it's the same thing as the minus gamma I term in the SIR model. So it characterizes how long the person is infectious and how long it can infect the others. So this is a combined regime, and it was predicted by Vasquez in 2006, this type of growth. And when he actually modeled this epidemic spread by a branching process model and on a complicated network structure. So some way he expects the network structure, contact network, is affected, and it's more, it's changing in time. And his model predicted this type of ansatz. So we look at here the data from Czech Republic, and here we have three plots. The first is the linear plot, so both axes are linear. Second was is the semi-logy scale plot. So the vertical axis is logarithmic, but the horizontal is just linear, and the last one is the logarithmic, double logarithmic plot. And what we see is that the green curve, it some way follows exactly, sorry for this, I need to avoid this. So the green curve follows this law with fitted parameters. There are three parameters you need to fit. Is A, capital A, which is some way the size, alpha is the power law exponent, and TG is this time scale, which is kind of important thing. And we see on these three plots that the data fit pretty well this curve. Okay, from my perspective, this is a pretty good fit. And it's just three parameters. You may say, oh, three parameters. Okay, that's the 20. You can fit an elephant, if you have enough parameters, but there's a couple of features. So let me explain what are features you see on this graph. And the red curve or red line, vertical red line, points out at the point where there's a peak, epidemic peak, so the maximum. The blue is the inflection point. Okay, inflection point on the logarithmic plot is not that efficient, but you can see it over here that is inflection of the green curve on the first plot. That's the inflection point. And the small lines you see over there correspond to the mitigation measures they use in Czech Republic and the dates where they applied. So there were, three gray bars correspond to 3 days where they applied the mitigation, the major mitigation, measures. And the purple one, it's 10 days after the first mitigation measure, the major mitigation measure. So what we some way see that about 10 days after the first mitigation measure, you some way approach this regime. A previous regime, some way we don't show here is the exponential regime over here. The first is exponential, then you have the power law growth. You can see it on the third picture, and then you go to this power growth exponential decay. Okay, so that's some way the story, which we believe is present in data all over the world. Okay, and it all differs by the parameters and when the onsets of individual stages are, but we some way see this persistently in all the data we look at, and I really mean all the data. Some countries show really random changes in the data, in that case, you typically need to look at the data more closely, and very likely the number of recovered cases is not reported properly. What they typically do, they report it in batches. So, for example, they report the recovered cases only once a week, or they have only once in 2 weeks, and so on. So you do some kind of smoothing on recovered cases. You don't smooth the other data, and you see trends. Actually, just to avoid any problems, there is some smoothing, but really local, only very local averaging for 3 points, just to avoid, the problems and to make fits looks a little bit better. But you can do the fits on the raw data if you want to in countries which report properly. On countries like Germany and so on, the fits are perfect on the raw data. Some countries, of course, their reporting is tricky. So this is Czech Republic, but that's not probably what you are interested in much. We will get to more countries. But what actually the ZIF and ZIF, as I said, the first study was, he was not even looking at the data of the active cases. He was looking at the deaths, and he saw this power law growth and then the decay, possibly the decay. He matched that data as well on the deaths from China. Okay, Chinese data, I'm really don't want to comment on those. So, but at that point, he got a really nice match, and it was possible. What I want to remind you of by this slide is that if you take any data from COVID, which actually are able to have a decrease in some sense, so the daily reports and so on, the trends I show you are present in all the types of data. So it's not just one part of the data. In some way, it's a natural part of the data. It's something in, deep inside of it. I'm not explaining why it's there. I'm just saying it is inside, and we can observe it in all types of data. So I want to now jump to more countries, and again, this may be a long survey of those. So these are the countries which on May 5th were, or May 8th, I think maybe May 8th, were in the growth phase. So for them, the green line is some way showing the possible outcome of the epidemic, some way. So what's going to happen with them? And we saw, like Belarus is over there, and we see they jump up on that curve. Below is Canada, which is following it as well. Hungary, we also see the purple bar, which some way correspond 10 days after the measures were applied, and that shows some way we got close to the green curve at that point. For Netherlands, we see as well, just some kind of identification of that. Again, this is good for monitoring the stage at which country is at this point. Okay, so these are 4 countries, and all of them are beyond the inflection point and be in front of the still they didn't reach the maximum, the peak of the epidemic. These are the good countries, because once your data are in between the inflection point and the peak, our predictions are pretty precise. I will show you the reliability of studies in a second, but what I'm saying, once you reach the inflection point, all the predictions are much, much easier to make than if you are in front of if you didn't reach the inflection point, it means that there's no systematic decay in your data. It's very hard to tell what decay you expect in the future. Okay, so that's really like some way important, because in many countries people ask, can you tell us when is going to be the peak of the epidemic? And what I'm saying some way is here that solely from the data is impossible. Okay, you may have a model, some kind of model which may, predict what's happening in the future. But if you're looking, it's hard to make any predictions about what's going to happen. So that's tough, because for these people, it's really difficult to make any estimation. Although we observed many countries, and we came with some heuristics. And one of them was, for example, that if you follow the country which didn't reach the inflection point, that many of the, almost all the countries showed the trend that the power law growth connected to this regime PGED, this power law growth with the exponential decay. It connected very close to the inflection point of the green curve. So that helps. Also, we can estimate the parameters from the other countries, from similar countries, and it seems like some parameters are pretty universal in the sense that countries do not spread, do not have a large variation of these parameters. So if you use all these helps and hints from other countries which are ahead of you, you can make a good predictions. We were some way very successfully predicting Slovakia. And at the I think at the end of March, we predicted about 1,000 cases peak in Slovakia at the end of April, beginning of May, and that turned out to be true. And at the time, the predictions by the SIR models of the other types were predicting hundreds of thousands of sick. So this was pretty efficient. But there's a warning. I really want to put a warning over here. We are predicting and we're discussing only the data. We're not telling anything. I'm not saying anything about what's the number of sick people or infected people in the population. That will be the second part of the talk. Okay, so right now I'm not making any claims at all about what's really happening in the country, in the population. I'm saying these are the data, and I want to predict the data based on the trends I see from other countries. Okay, so these are two different things, and you cannot mix them. The data do not necessarily provide the information about the real state of pandemic. So this is, this was for me like the crucial thing to see. And although we are pretty good with data, to estimate the, how big is the epidemic in the country, it's a very different task and very different question. So anyway, so what I'm saying right now is that even in the case you are, at the beginning of the data, somewhere you see the parallel trend, you may be able to provide pretty good estimates. Although, there's heuristics involved, which is, who knows. No, but it worked. It just worked in one case. We predicted some other countries, it worked as well, but, we don't have, any, very systematic way how to do that. Once you are behind the inflection point, this is very systematic because you can really, find a good green curve which fits your data, and then, that is pretty reliable. Again, I will do the reliability study in a second. So I'm again coming back to the previous, mess up over here. So because I'm not in presenting mode. Okay, so these are more countries you can see over here. I want to discuss just, what you see already. Andorra is perfect. It's a small country. Austria, it was like perfect example of our, fit. It was just a perfect fit for a long time, but then some way at the end of April, they alleviated some of the requirements, some of the measures they had in Austria, and then you see the the change of the trend. So what it means that of course the data are some way assuming that the country is following some type of measures, and it's hard to tell. It's individual for each country, but all countries are some way using the same sequence of the measures. Not all of them, of course, but the sequence is some way similar. So it's inside of the data that these measures are some way built in. And in Austria, we see there's another thing, and also in Australia, as you can see, Austria and Australia as usual, as Slovakia and Slovenia are quite similar. And you see the similar trend almost at the same time. They decline, they diverging from the green curve, and that's because the measures are not anymore in place, not so strict and so on. On the other hand, Croatia, okay, they stick with those measures at least on that date and so on. So these are a couple more countries, and oh yeah, we can look at more. And it's interesting that bigger the country, more cases, they're more robust for our estimates. So Israel is a perfect case, of course, but Italy, you see, it's really following beautifully, and Japan as well. And there's the Slovenia, which was pretty good. Okay, I don't want to spend too much time with the countries, but there are many countries. What I want to say is that you can see that this is a global thing. It's not just we studied 120 countries and we fitted 118 of them. One of them was didn't work. Was I think Mauritius, because they were in complete lockdown for 2 weeks, and they even closed the grocery stores. Okay, so we couldn't fit those. Okay, that was, we could, but we didn't trust that country. So, and UK, because we didn't have the recovered cases data, because UK is not reporting. So more countries, and now you see there's a kind of second wave coming in some of the countries, Azerbaijan, Chile, Iraq, and Jordan. And yeah, something else is happening over there. I'm not going to discuss that because that's way beyond the scope of this talk today. So there's something happening over there. They probably imported too many cases, or they did something wrong. Something is really happening with these countries, and now more countries are doing it, but at much lower level than say Chile, who got this at the time of peak, which is really bad time to start the second wave. Okay, so that's the regime, and what I want to say something about it. I want to say something about math behind this, and what is really interesting is that this polynomial growth, okay, this an exponential decay, this is not consistent with the SIR model as it is. But if you plug in, this type of ansatz into the SIR model, you figure out that actually it corresponds to the changes, temporal changes in the relative reproduction number are not, and it some way says that the relative reproduction number really decays as 1/t. So this regime corresponds to the algebraic decay of the relative reproduction number. So it some way says that the measures, the implied measures, the strict measures, some way reduce the efficiently reduce the relative reproduction number algebraically like this. And okay, this is good because once you know what to do with R0, then you actually can go back to the SIR model and build in this ansatz into the SIR model. So some way we were able to put all this parallel or polynomial growth inside of the SIR model some way externally, and it worked, and it really helps to. If you want to just modify the existing SIR models, then you can get much better predictions, at least at the time. Okay, so this is the relative reproduction number. The question is how long this is sustainable. As well, you can see that as t goes to 0, then the relative reproduction number goes to infinity. This is some way very similar to the graph theoretical approaches, which take the fat tail distribution of the degrees of the individual modes of individual nodes, and then typically if you take gamma between 2 and 3, the parallel decay of the number of modes with a given degree, so the super spreader effect, then typically this distribution has infinite mean at the beginning. So this is some way correspond to that. That's the same effect. And then there are these models where you eliminate the highest level or highest degree nodes from the model, and because these are getting infected, and then that may be source of the decay. Sabo published a preprint quite recently where he actually uses this type of model and getting very similar results. Okay, so but that's not what I want to say. I want to some way conclude this section, at least the mapping. I will show the predictions or the reliability study. But the 3 phases you may expect in many countries. So there's this initial exponential phase, which is coming from the SIR model. Then there's this polynomial growth phase, which, okay, hard to explain what it is and why. Okay, I have some understanding of it, and I will explain it later, but not now. In data, we see it, and I cannot explain it. And there's this final polynomial growth with exponential decay. And this is written in different parameters, but it's the same thing. So that's the trend in the data, and we believe it's pretty good. So here are coming, going to the predictions and some kind of validation study. So what you see over here is 8 different countries, and we withheld number of data. So we withheld 15 dates, but not last 15 data points, but 15 data points before the country reached the top, reached the peak. So we are asking whether we can predict the peak, the time of the peak, and the size of the peak of the outbreak, the max. So the epidemic size, that's how they call it, an epidemic. And we see that in countries like Belgium, the estimates are pretty good. The red rectangles, they showing, how good is the estimates. These are 95% the confidence intervals of these 2 parameters, the time and size. And you see Belgium is pretty solid, and less and less data you withheld. So then the rectangles are inside. So you're making your estimate more precise. The same in Portugal, but you see some kind of drift. That's a picture E, in the bottom. there's some kind of drift, and the more data you have, bigger is the peak. So there's something was happening. For Italy or for some other country, I think Israel, it was going down some way. So it may go the other way. Switzerland also worked very well. The good example is B, is the Belarus, which was only about to reach the inflection point. Okay, in the data I showed you, it was at the inflection point, but now we're withholding 15 points. So we're making estimates 15 days before the inflection point, and you see the squares are pretty big. But anyway, still it gives you the range, at least the order of magnitude of the epidemic size. Pretty good, okay, approximate. It's not perfect, but okay, you don't have that much data for Belarus. For all the other countries, okay, it shows pretty well. And we made this, this check consistently for many countries. So Czech Republic, for example, was in some way, the peak came much earlier than expected from the previous data. So some way, probably their mitigation measures were a little bit more strict than some other countries. Who knows? I don't know. For US, okay, it was shifting and shifting and shifting. I think it's shifting still because their mitigation measures are not that great, as you know. So this is some kind of check. There's one more picture I'm showing over here, and it also provides the confidence intervals to their all time later. So for Netherlands, we made at the beginning, so we withheld all the red data, you can see, also plenty, there's like 20 days withheld, and we made the 95% confidence interval of the future evolution through the whole time of pandemic. And you see, okay, I'm just saying this may be used for that. And also for Italy, you see we were within that. And for Switzerland, we were able actually to follow the epidemic much further. But over there, we use the estimate only 7 days before the peak. So we are cheating a bit over there. There are 2 online tools which were programmed by our friends, which are, which I think coded the data for many different countries, and you can see how they evolve, what are their predictions, and so on. So these are pretty cool tools, and yeah, thanks for Lukáš and Michal and their friends work on it. Okay, so so this is the end of the first part, and this is all about the data. But here's the question: we can predict the data, but does it really matter? Is the question, because we know there's a lot of uncertainty in the data. We know there's, I will again list, many of the aspects, but is the data really so reliable? Now, this is what is getting really controversial, because many people take this data and based on them, they build a model. They say, oh, there's something happening with the graph of contacts, or there's something happening with, who knows what. But I would be really cautious, because to make any predictions based on this data, you need to take into account many very special features of the whole coronavirus, of the testing, of many different things. And if you neglect some of the key parts, all your analysis may be just completely wrong. So I'm not saying there's all this research is not useful, but I'm just saying be careful, be extremely careful to interpret the data you see, because the interpretation of the data may be tricky. So as I said over here, we can predict or work with the data. We understand what the data is showing, but I'm not really sure it shows the extent of the pandemics and what's really going on. So that's why we actually tried to address that question as well. So very likely the data do not provide the information we need to justify our models, to calibrate our models, to do anything. So the data are really tricky. I'm not even talking about cheating of the data or like false reporting. Oh man, this is a big issue in many countries, and gosh, it's complicated. So I will now really briefly discuss a couple of aspects which I really think are really tricky. And okay, this is really, if you haven't seen some of these studies, you may be really shocked. Okay, some of them are preprint, some of them is already published research, but okay, I will go really quickly. So first of all, it's a quite recent study from Italy, when they look at the seroprevalence, so the antibodies. No, this was not antibodies. They were looking at the antibodies. That's right. They were looking at the antibodies in the blood of the blood donors. Okay, so easy study, but they looked before the pandemics. Okay, they didn't look at the pandemics, but before the pandemics. And what they some way are showing, two pictures I want to point out, is over here is this figure 1. And figure 1, the first 4 bars correspond to the prevalence of the antibodies of any type, IgM or IgG, in the population. And it shows, okay, 4 bars, white and, like getting darker from the left. And the white one correspond to time and when they registered some of the first cases of the coronavirus in Italy. So it means at the time where they were registering first cases of first confirmed cases, they already saw 4.5% prevalence of the COVID-19 or whatever SARS-CoV-2 antibodies in the blood of healthy blood donors. Okay, this is mind-boggling. Okay, so it says that some way they measured too late. They got the outbreak much sooner than that. Okay, so you say, okay, this is just the first week, but okay, let's look at the other data. So this is other data, and this shows the progression from this. Again, we're looking at the left diagram, or maybe this is the good one. This is the picture, the right diagram. It shows you EGG and EGM. EGM correspond mostly to active sickness, while EGG is that you are behind it. And we're looking at dates. Look at this: December, January, February, March. We're looking at 2 to 3%. They use the ELISA test, which has 99 point something specificity. So this is, the measured percentage is order of magnitude higher than the specificity limits of the test. So this is a really statistically significant signal. So it means that, okay, we see the outbreak coming in March and April, but remember again, this, it takes a while till you develop the EGG. It may take to 14 to 40 days till you develop these antibodies. So it says, okay, there's there was something going on in Italy for sure before, in January and December. We don't know yet what was it, but some way the data, there's no zero. It wasn't zero for sure, at least. This is showing that the number of cases was not zero at that time. So that's the first study. So there's another study, which is quite an important one. This is already published in Annals of Internal Medicine, which is pretty solid journal, and they're looking at the PCR test. RT-PCR tests are the tests which are used to detect the confirmed cases of the virus. And okay, I will skip this picture because they did the meta study of different studies, but this is the picture which is really important. And the picture on the top shows the probability the PCR test will be negative given the patient is positive. Okay, so there's a probability that the test will be false negative even if the subject is positive. And this is on the bottom, on the horizontal line, is the days since exposure. So we see what you probably heard, that the first couple of days, first 3 days, is the incubation period, and you cannot detect the sickness by the PCR tests. Okay, that's okay. This is okay. This is accepted. Okay, then it goes down, but you can see that even at the top, at the peak of the sickness, where you have a maximum load of virus inside, there's 25% chance, or even more, 30%, 40%, who knows, that you will be false negative. Okay, so it means that the PCR tests have a really strong limitations. Okay, it's increasing a little bit more later on, but goes to actually it's getting worse. Okay, the false negative may be almost 50% after 14 days. So it shows you that you have a really small window for each patient to be positive, and not only that, even during the small window, there's a huge chance you will be false negative. Also, you may get false positive, but I don't want to discuss that now. So there's also the temporal dynamics of the shedding of the load, of the virus load people have. Okay, this is another study from Nature Medicine, which was published about a month ago, and it shows you the individual paths of people who have, they study their viral load in their PCR tests every day or every couple of days. And we see this decreases, but it's not the mean which is important, but you see the individual trajectories. The thing is, there's a huge variation. So if you get sick, the load you have in your throat and in your upper respiratory tract is changing rapidly, and it may go even up, after a few days, and many different scenarios are possible. So this is really complicated, because how you tell who is sick, how you tell who is sick in general, what does it mean to be sick? Okay, so this is really complicated issues and go to the details of the medicine and so on. So it's not easy. And there's one more study I want to show. It's a very recent study which appeared like 2 days ago. Is the immune response, and this is Kellam in Journal of Virology, and this is a review paper, and it shows how in general it looks like. And you see that we may have the blue line or blue curve is the infected but not detectable antibody response. There may be plenty of people who are not detectable by any type of tests, and there are the EGG tests may be relevant for some time, but if you have a low response and low number of the antibodies, you may be actually detectable only for a short period of time. The end is estimated to be about 40 days after the infection. So if you were sick in January, in March, at the end of March, your antibodies are not detectable. That's many data show that. Actually, some data. So it may be a pretty complicated thing actually to detect. So let me move on a little bit. And so this is the picture you may have seen before. This is Australia, and this is the website EpiForecast, which actually, based on the data, predicts how the epidemic will look like, and it shows you how the R0 looks like. Okay, so probably in Australia, the R0 was decreasing from this value of 2 at the beginning of March, reached 1 at March 21st, then decreased, and now it's increasing, and it's close to 1. This is what data showed us. But the thing is, okay, let me show you Slovakia next. Okay, let's see what we got for Slovakia. Okay, it looks differently. As I told you, we're doing really well. Daily cases 30, 60, you see the number. It's impressive. Like right now, we are in these zeros here. But effective reproduction number for us was predicted to be, in between 1.5 to 1 from March 16 to April 13, then decreased, and now is who knows where. So, but other measures were introduced on March 8 to 12. So on March 2, between 8 and 12 March, other R0 had to decrease really bad, and afterward, people got really more active. So this doesn't make any sense from the, if you think about what R0 represents, number of contacts and so on, and we don't have many the susceptibles didn't decrease significantly. So how come, what's going on? This doesn't make any sense. And here's the, the data from Apple, which show the mobility of people. And we see that at the time, this is almost not completely overlapping times, but we see at the time where the R0 should be close, close to 1. Actually, what we did, before, okay, this is March 8, during that time, there was a huge drop of activity and mobility of the people. So there's no way R0 stayed about the same. So, what I'm saying, this prediction of R0 is just garbage. Okay, it's just coming from the data. Okay, it's showing what R0 is in the data, but it doesn't correspond to the real R0. Real R0 had to undergo really different changes. And now it's increasing, not decreasing. They say from April 13 to 20, there was a decrease. Come on, the activity really, it was increasing at the time. So it's really just, that doesn't really make any sense. So what one can do, so a realistic model needs to, in our opinion, take into account limitation of testing, both PCR tests and antibody tests, a lot of limitations. Effect of testing, because if you test somebody, you isolate that person, so that needs to be taken into account. The mitigation measures and social distancing and changes in contact network are really important. A lot of people are working on this. These modes of transmission of infections are very different. That should be somewhere over there. Special clinical properties I mentioned, these different behaviors of the viral load and variation of viral load is really important. And this earlier start of pandemic should be taken into account, all of that. So that makes it almost impossible to make a model because, wow, so many things and, you know, a lot of uncertainty almost in any point I made up. So this is complicated. So realistic model, what we consider important is testing and is viral load and earlier start. They need to be taken into account. So let me just now very briefly discuss our very recent model. It's going to be like just really a couple minutes. So we will take into account that we will have two type of people. There will be people with high and low viral load. There will be dynamics of infection. So people may jump from low to high and from high to low, also, you know, due to the contact, but also through the individual behavior of the sickness or the disease, you know, in the individuals. We will have natural delays in transmission. We will have testing by three types. You know, the people who go to the hospitals are tested. Then we will model contact tracing in details, which is, wow, it doesn't look very easy, but we did that. And also there's going to be random testing. We will look at the delays in testing and also the limitations of the tests. So that will be the model. RNA we will some way take as taken. I will show you in a second how we do this. For example, contact tracing, this is just our picture for the contact tracing. This is the calculation we make. So we trace, you know, it's on average is a mean field model, but we're looking at, you know, who you met, how many days back, and how these people advance in time, you know, through the epidemic. When you're testing them, what will be the outcome of the test? Okay, so there is some kind of a lot of formulas, you know, hidden in this one picture, but you know, that's just the contact tracing. You know, each part is, you know, has some tricks. The good thing is it's a lot of calculations, but not that many parameters. So it doesn't look like it, but there's really not that many parameters. So, and here's the last picture I want to show you, because I'm not going to show you more details of the model, but I show you what how we see what happened in Slovakia. Okay, so here in the right hand corner, right top corner is R naught. R naught we don't calculate R naught. We input the R naught. So we believe the our R naught was constantly about 2.6. That's the estimated number. Okay, maybe 2.8, maybe 3. Who knows? I'm not sure about it, of course. But I'm saying until, you know, we recognize any problem, the R naught was not changing. It was just a normal one. Then, you know, we had these measures. During these measures, it took about 7 days to adopt them. We decreased our R naught, and now we are actually our R naught right now in the horizontal axis. This is 0, it's the 1st of January, so end of May is 150. So our R naught is actually already way about 1.5. Way about 1, close to 1.5. If you go outside in Bratislava, you would see there's really looking like R naught maybe 5. You know, it's just you know. The measures are not, you know, schools are closed though. So what I'm saying, you know, we take this R naught as an input. Okay, the other input we take is the number of tests. We're looking at, you know, these are the real numbers of the test. We ramped up the test, you know, some way. First it was, you know, almost no tests or almost no tests. Then we had some small increase, and then we were increasing it. And now this is pretty huge. Actually, this is a lie, because the number of tests now is decreasing rapidly. It's unimportant right now. And what is over here on the right hand, on the left side, is the results we're getting for our model. So what we see are two pictures. The top one is the number of infected in the population. This is what we don't see. This is the real number of infected. In the bottom is number of confirmed cases. So these are the data we see. You look at the horizontal axis. This is like 500,000, 1,500. Over here is times 10 to the 4th. So over here, this is like 40,000 or 60,000. And so we saying there was a lot of sick people in Slovakia we didn't test. We test them, maybe some of them, but we didn't recognize them. The yellow bars show, or yellow lines, vertical lines, show the difference between the peak of the real epidemic and peak of the epidemic we see in the data. There's a delay about 40 days. Okay, so we believe actually our epidemic had a peak when we started to introduce the measures. So we're saying we haven't seen these people because we didn't test. So we couldn't see actually the epidemic because we didn't make any tests. We had we made, I think in whole February, we made 180 tests in general. And these were people, you know, these were very specially selected people. So, and the thing what we some way saying that the blue line are people with the mild symptoms, so the low viral load. There's plenty of those. There's also people with high viral load. These are people who we see in the hospitals who get sick. Also, people may get high viral load for a couple of days during the, their personal, in the evolution of the disease in their bodies. But some of them, go to the hospital, some of them not. So we have a constant, in the model for that. And we see over here that, the number of people with high viral load was not that big. Okay, although, pretty big. But we see over here in the number of confirmed cases, these are the people who go to the hospital. So we may fit those as well. So we're not fitting now only the data, which we see the number of reported active cases, but we may look at how many people are in the hospitals. And we also may fit the number of people who are dead over there. And we can fit all of it simultaneously. Okay, and so I'm not saying actually this is necessary exactly what is happening. I'm just saying this is possible. It is possible that the data we see, the lower picture, may not actually contain the proper information. The proper information, there's a delay, there's a lot of things, which is just the effect of the testing. Okay, if you just put the ramping up of the testing into the model and the reliability of the lower reliability of the tests, and the jumps in the R0, if you put into your model, then you can see effects of this type. What it means is that if you base your mathematical model on the data which is available, you may be completely off. You may completely miss the important parts. Okay, and I think this was almost so this is just the comparison of the R0, so this is the R0 from the website, and this is the R0 we're putting in, and you see that the trend is just completely different. Okay, this is aligned again for the same times, and with some way. Okay, at the end, actually, quite recently, because we're testing enough, we have a low number of infected. Okay, these things are agreeing now. But at the beginning, oh man, I think these were completely different things. Okay, so thank you and good luck, and I will stop over here.
Thanks a lot, Richard. That was compelling. There's so much there. Let's give you a clap. I'll count down 3, 2, 1, and thank you. So I'm sure there are lots of questions. Would anybody like to start?
I said it's controversial.
No, I'll shoot it off. So I mean, the first part of your talk. Okay, there's a question from Sarah, but I'll start. So I'll just say it. I'll say mine quickly, and then Sarah's. So first part of the talk, you were a statistician, not an applied mathematician. Right?
Yeah.
Yeah. And now, in all these fits, did you use parameters jointly estimated for neighboring countries or for countries that have similarity? So were there covariates, or did you fit for each country individually the 3 parameters of the PGE?
Yeah, so we fit the parameters for each country individually, and if you take the preprint, the numbers are published for all the countries. We see similarities. Actually, countries which dealt very good with the outbreak typically had very low number TG. So this time scale. So they were really efficient in removing the what is it? I need to now use the right terminology, because they were removing the active cases into removed cases. Okay, because that was not necessary. Of course, it depends what you can achieve it in the data many different ways. So the countries which did this well, they had the parameters very close to each other. So also the powers were, the parameters alpha were in a very narrow band of values for a large number of countries. So there are similarities, and one can do the statistical study on that for sure, like even the region. We didn't have time because once we got the data, I was more interested in understanding the real pandemic. So unfortunately, we didn't have enough data. We may come back to that later. But right now, I was more interested in the second part than the first part, because I felt like, we have enough understanding of that at that point.
So you treated the first part of your research was kind of motivating to build the model, or it's exploring.
Predictions. We were really motivated by predicting the data. because there was a really, I don't know how in Australia, but in Slovakia, this was a big issue in politics. So there was we had this government model which predicted first, I don't know, 2.5 million sick people. Then the second version, which was 150,000. There was already our equations, but we didn't put in the values, the fit parameters. They put very high R naught into the model. These people who are modeling it at the Health Institute. And then, at the same point, we had the prediction 1,000. Okay, they were talking about 150,000 sick and we about 1,000 sick. And we were looking only at the data, but the truth, I don't know, maybe we had 150,000 sick. We don't know. So the problem is with the data is that, okay, we can model the data pretty well. Okay, I was satisfied with that. I'm a mathematician. I want to succeed. I wanted to predict the data very well. We succeeded, and it's not that interesting anymore once you realize you're predicting something which is maybe not completely relevant. So it's a win, but it's a lose as well. Loss at the same time. So yeah, that's why we are not. We stopped working on it. Although we could do a lot of data mining out of that. But we are more interested now about what is really happening.
Thanks. So Sarah asked a question in the chat. Do you expect Australia to encounter a second wave?
That's a really great question because I have no idea. Okay, so any predictions of the second wave are really, I cannot imagine anybody makes any predictions of that, because what the second wave means is that, it may have many different sources. It depends how you open your borders. Do you allow the people to come in and, who can spread the infection, or it may be hidden clusters you didn't discover because, as you see, the meat factories and the church and, other, close communities may produce and may be unnoticed because they're asymptomatic. According to our knowledge, actually, even asymptomatic patients, some of them, if they have low immunity, may develop high viral load. If you have high viral load, you may become a super spreader. If you become a super spreader, you may become a super spreader. If you are at the same point super emitter, so it means that you emit a lot of particles when you're talking. Then if you go into a potentially super spreader event, then you have high load and you are super emitter, man, then you have South Korea and you have other things, So how can you predict any of this? I don't think so. Anybody can predict. What we see actually is that at least probably I can say the antibodies, the levels of antibodies we see in the population, even in the model, even when we have this increased population, are not sufficient to guarantee the herd immunity. But again, on the other hand, many people say that it's not the antibodies, but it's the natural cell immunity. So the some way the natural response of the say T cells to the viruses, which is more important. So no, the second wave, I doubt any estimate, anybody who makes any predictions. That's very stochastic.
Thanks. A question from Mahan, I'll just read them out as well. So as you said, there is a lot of controversy in data published by the countries. Have you tried to adjust data based on number of testing, active cases, mortality, and etc. to generalize them across the world?
That's again, that would be a great study. We didn't do that because we didn't. So, like if the question is, adjust it according to testing, it's a problem. It's a significant problem because the problem is in data reporting. If we trust the data and they are reliable, then one can look at, more facets of the data, some way more dimensional data. But the problem is the data itself are not that reliable. I don't know, in Europe, this is known. For example, Belgium is reporting all the deaths in the hospitals because according, to the information I heard, in Brussels, they have really good understanding of how the money will be distributed after the pandemics to the individual countries, and more deaths means more money. In countries like Slovakia, we want to be best in Europe. We don't report all the deaths. So what about, the tests? It depends how you perform the test. The nasal swab is not that easy thing to do, and it's not only the number of tests, but who you are, doing the test to. So if you can test the random people, you do 10,000 tests, It's the different thing if you have the right group of people to test. So it's not the sole number of testing, it's the who you test. And that's not reported anywhere. Okay, probably if we search the data for some countries, you can get it. We know a lot about, we have a lot of data about Slovakia, and more data I have, the more I see this is like from data, it's impossible to get any more information. So yeah, it is possible. Probably, after the epidemics in coming years, many people will look at it. But right now, I think it's more understand the medical and clinical issues. I think that's more, it's a bigger part of the problem, and the testing in general, how the testing influences the other thing. So we didn't adjust the data. That was just the pure data analysis, the first thing. And the second is the model, and we take the number of tests into account there, for sure. And it seems like it's working very well, but who knows? We may be completely wrong.
Thanks. So there are two more questions. Chantal, do you want to just say it yourself, or?
Thanks, Yanni. Thank you for the very interesting talk as well. So you basically answered this. My question was related to Mahan's question. And I was just wondering, how can we understand the real pandemic if the data is highly biased, and what can we still use to inform our modeling, and is there some information that can be retrieved from the data? So I think you've partially answered this.
I hope I answered that. I tried my best.
Yeah.
All right, and I'll read Jana's question. I think you know Jana probably even well.
Yeah.
I kind of second Jana's question. And then when it comes to shaping policy responses, is it more important to model real cases when these cannot be somehow measured or proved? There seems to be some value in modeling what is being measured, even if it's not the truth. It's almost philosophical, but it's not. So, so what's your answer to that?
I don't know. I really have no understanding. So for me, I'm really worried about the wrong interpretation of data. I've seen so many papers who try to understand the data by, I don't know, like, look, this is what's happening. This is the mechanism behind it. And they don't take testing into account. They don't take the test limitations into the account, and the delays into account. So yeah, I'm a little bit worried more about that part. What we can say, it's not that bad. For example, we are now working with the National Hematological Station. When we want to test the same as in Italy, the serological studies for the antibodies of the archived blood from blood donors. And so I think studies of this type may be really important in the future. And I think many countries will do that, because that's a really good sample of and a representative sample of the society, of the population. So because it's completely unbiased, these are just, blood donors, very healthy subjects. And you may look into the past and check, what the prevalence is. The thing is that, because of this limited how do I say, longevity of these antibodies and of the viral particles, if you look into the archived blood, you may see what was the stage at the time, which you cannot observe right now. So I think studies of the archived blood will become very popular and very prevalent in the research right now. And that's actually the answer for Jana's question, because then you can model actual data. Because it's what I'm saying, the data we're getting is polluted too much by the effects we cannot take into account. You will have better ELISA tests for the antibodies, which will have that will be not just the nasal swabs or something like that, but it will be like pretty reliable laboratory tests of the systematic samples. So I think that's the necessary part. And then the modeling should be done on those data, these data. And you can use the data as a proxy, as I was using the data of the country, what outcomes, what trace it leaves, given the processing of the data through the other types of testing. So I think these approaches will arise, more and more. But I think the testing is really the crucial part.
Thanks. Okay, it's 9:10 here. That's almost time for tea for you and Bratislava. There's one last question. Sorry, for
lunchtime.
Lunch. Okay, so you don't eat lunch at noon. So just last question from Mahen. What is the window of having real positive and when? I'm not sure I understand it, but maybe Mahen, you just want to ask yourself.
You mean, yeah, please.
I was reading on the chat, but Mahen, did you have a question? What is the window of having a real positive?
Okay, so I will try to answer that. So it depends on the tests, but if you're talking about this RT reverse transcriptase PCR test, so these are the tests which are used for reporting the confirmed cases. So it depends. If you have, I may go maybe back to one of the pictures, but let me just visualize it here before I will spend time to look for that. So if you have a people with high viral load, it's believed that the PCR tests may be positive for maybe for a week, maybe for longer. So it is until you still have a large number, larger load of the virus, of viral particles in your upper respiratory tract. For the lower loads, it's unknown. For example, for the kids tend to be negative on PCR tests. It may be because their load is too small. So, and it's not that you're not gonna detect it by the by the PCR method, because PCR method can detect up to one particle in the sample. The problem is the limits of detection of the PCR method, because of the eventual contamination of the kids and of the many other things, are set much higher. So I don't know. It's actually the measure they use is called CT, so number of cycles, and typically the WHO reports that the positive sample should be 40 CTs and less. So it means that you see enough multiplicity of the virus if you do less replications. So up to 40 CTs should be should be positive, and over 40 up to 45 should be negative, and then over 45 nobody does, because that's homeopathy. Okay, but here's the problem. Typically there's a lot of samples around 40. Okay, and it's really hard to tell what it is. And for example, it's known that the kits for PCR all around the world were some kind of polluted and contaminated by very low dosage of virus. It's because of the validation studies and because of really fast spreading of the virus. The virus is actually, apparently the virus is spreading very efficiently. So if you open a vial with the virus in a building, you may contaminate the whole building right away. So it's really like with one molecule. Okay, so, statistically. So it's not that easy actually to make the tests much better, because you need to take into this thing into account, and that's why you're setting the limit of detection around 40. And that means that you will lose a lot of cases which are on that level of load. And also you need to be careful about the nasal swabs, which actually are not that perfect. So my estimate from the studies I've seen, I'm not epidemiologist, virologist, or anything like that, but I've seen a lot of papers on this topic. I would say for majority of the people, these PCR tests are positive only for a couple of days. And this is like few days before the onset of the symptoms and few days afterward. So maybe, up to a week. For some people, it's longer. For some people, it will be shorter. Some people will be undetectable completely.
Okay. Thanks a lot, Richard. This was fascinating. A lot of information. Very nice. Let's thank you again. I'll count down 3, 2, 1, and thank you. So this will be up in YouTube, and we still don't have a speaker for next week and the weeks to come. If anybody wants to take a reading seminar type of approach, as we've had a few weeks back, please feel free to do so. And thanks again, Richard. Bye-bye.
Thank you. Bye.
Thank you, Yoni and Richard.